between September of grade 8 up to April 30th. Linear service will be in grade 11. Above our graduation work experience course. If you have any questions or you need to pick up a form, please stop by the Creative Center. All community service hours forms are due by April 30th, 2026. Good morning. Good morning, our leadership February. Relay the Light is here at USS. Relay the Light is an event that will provide you're looking for the event will take place on April 6th from 2 to 6 p.m. at our school library in Houston. There'll be a free t-shirt, free unlimited food, but afterwards it's open activity. An amazing project. Tickets are only $50 for an unforgettable experience and participants every now and then.
If you guys did homework, I also felt like I found that either wait, isn't like the gas? Isn't there a
What? So we're not going to spend any time really doing this other than we're going to look at the pictures and do one example and then we're moving on. Yeah. Okay. We did this in January. Okay. So we are not spending much time on this at all. Precipitation reactions. This is about net ionic and complete ionic equations. So we're going to spend like 5 minutes on this and then we are moving on. You will be doing this 3.1c for homework because, you know, complete ionic and net ionic equations are something that you need to be able to do with your eyes closed. Yes? So make sure that you do understand it. But just to refresh for you, what's going to happen is you'll have an aqueous solution with free-floating ions. You're going to have another aqueous solution with free-floating ions. You're going to mix them together, and if all goes well, you will end up with a, what do we call this down at the bottom? A precipitate. Please make sure you can spell that word. This is a precipitate. How do you abbreviate precipitate? PPT. Okay. Yeah. And a precipitate is what state of matter? Solid. What do we call all the other ions floating around in there? Spectator ions. Okay, excellent. So what you do is, actually, we're just going to go through the other two examples. Two special cases. Free-floating ions plus free-floating ions. This is on your next page. And we get two precipitates. Yes? And if you have two precipitates, there are no spectator ions. All of the ions end up in the net ionic equation. Are you guys okay with NIE? What does NIE stand for? Net ionic equation. What does CIE stand for? Complete ionic equation. So the CIE and the NIE are the same. And what do we call this type of equation here where we haven't split it apart at all? We call this the formula equation. Formula equation is this whole thing here. Yeah, where we haven't shown the ions yet. Okay. And lastly, we have a special case. We throw things together and we get no precipitate. What do we do in that case?
Everything is canceled out. Oh, we have no net ionic.
And not just no net ionic equation, there's no formula equation, no complete ionic, no net ionic, because there is no reaction. And you cannot write an equation if there is no reaction. We have just mixed. This is a physical mixing. So if you do write the products and there is no precipitate, you should then cross them out, because by writing them as products, you're saying, I had a reaction, and you didn't. Okay? So you can just cross the whole thing out. There's no reaction, so there's no formula equation. There's no net ionic equation. There's no complete ionic equation. There's no nothing. Okay. Do you remember how to predict the products of these reactions? Solubility table. And which ions do you combine? Positive goes with negative. And which one goes first in the formula?
It's like the outside inside.
Yeah, so you do the outside and the inside. That way you end up with your ions in the right place. So if we look at our example on the next page, if we have BAS, which is aqueous, plus CuSO4, which is aqueous, we write out our ions, and we end up with barium getting together with sulfate, and we look that up, and it is a solid. Copper, we go backwards for our inside ions, so that the copper goes first in the formula, and that's also a solid. So this is a situation where we have two precipitates, so the complete ionic and net ionic will be the same, and there will be no spectators. Okay? If we have SR, NO32, and KOH, the SR gets together with the OH, and the K gets together with the NO3. You should be able to tell that at least one of these products is completely soluble. Which one? Without looking at a table. Strontium hydroxide or potassium nitrate, which one is completely soluble? KNO3, because all alkali, and who are the alkalis? Group 1. And who are they? Name an alkali metal. Sodium. Name another alkali metal. Lithium. Name another alkali metal. Potassium. And those are really the big three, yes? Like the other ones, yes, you can run across them, but they're not that common. You've got rubidium and cesium. But really, if you know these first three, sodium, lithium, and potassium, you've dealt with most of it, because the other ones are really not very common. Yeah? I mean, we could throw francium in there too, but it's completely radioactive and doesn't stick around long enough to do anything. So all alkali salts are what? Soluble. What's another thing that's always soluble? This time it's an anion. Those are your cations that are always soluble. What are your anions that are always soluble? Don't look it up. You know it. It's here. It's one of these. Is it OH or is it NO3? How do you guys not remember things? Especially when I told you way back when, you should know this. You should memorize this. Right? Like NO3. And the last one you should know, all, it's another cation. No, we've got sodium, lithium, potassium. All alkalis are soluble. It's another positive ion. It's not on the periodic table. It's a polyatomic ion. It's a positive polyatomic ion. NH4 plus salts are soluble. Please memorize these. There's only 3 of them. Yes, it is time consuming to look at the solubility table. You can save yourself so much time just by knowing these 3 rules. It just means that you don't have to think so hard. You can be like, bam, that's aqueous. Because it's got K and NO3, right? All right. Do we have anything down here that's always soluble in our NH4, 3PO4, CuCl2? NH4. NH4 is always soluble. So it's going to pair up with Cl. So that's going to be aqueous. And then we have CuPO4. And you'll have to look that one up. Although I will tell you, PO4 is right at the bottom of the table, the solubility table. Things at the bottom of the solubility table generally have very high or low solubilities. Low. Okay, things at the top of the table generally very high. They don't precipitate with very many things. Things at the bottom of the table precipitate with lots of things. So if I had to guess, I would say copper phosphate is low solubility solid. Okay, but you can double check. Let's go look. Copper phosphate, solubility. There we go. Phosphate. Yep. Look at that. Phosphate, the only things it is soluble with are the alkalis and NH4. I don't even like looking at hydrogen in this context because it's an acid, right? And you know that it behaves a little bit differently, right? You've got your acid constant for that. You've got your Ka value for that. So really, it's just those always soluble ones. And with everything else, it forms a precipitate. Hydroxide, almost everything is low solubility, except for alkali, ammonium, and strontium. And then we get into the ones where we've got, there's more things, right? There's not very many things that are actually, going to form a precipitate, and we're good to go. All right. Oopsie. Okay, there we go. Now, while we're on this last one, actually in this one, we knew that one was soluble. If we were to actually look up the strontium and the hydroxide, we would find that actually they are also soluble. So this would be a case where you have no reaction, right? So you would just not write a reaction. Now this last one, let's do the shortcut method for writing the net ionic equation. Do you guys know the shortcut method? Okay, let's learn the shortcut.
Well, we're supposed to find the solid, right? So we just take like copper from there and from reactor.
Shortcut to find the net ionic equation, you write the solid on the right. Cu3, PO4, 2. And then what would you do?
Well, you just search.
You just write the ions you need to get that. Needed to make it on the left. So how many coppers do we need? We need 3 coppers. And what charge is that copper? You do need to look at that and you would say, okay, I've got Cl minus and I have 2 of them. That means that my copper has to be 2 plus. So I have 3 Cu2 plus. And I also have how many PO4s? 2 PO4s. So I have 3 coppers, 2 PO4s. So I write 2 PO4, 3 minus. And those are both aqueous, yes. And it is important for this unit that you show your states. Yes? Okay. You should still be able to write the complete ionic equation, but I trust you to be able to do that. Am I correct in doing so? Why don't we just do it once just in case? Just in case. If we had to do the CIE, basically you just take anything that is aqueous and you split it apart. So we would have 2 times 3 is 6 NH4 plus. We would have 2 times 1 is 2 PO4, 3 minus. These are both aqueous and aqueous. We have 3 coppers, 3 Cu2 plus, and we have 6 chlorides. And remember, every single one of these things that is an ion needs a charge. So don't forget your states, don't forget your charge. We end up with 6 ammoniums. And we end up with 6 chlorides. And then our solid, we do not split apart, so that's just going to be Cu3, PO4, 2, solid. And if you wanted to, you could find the net ionic by writing the complete ionic first. And then what would you do to get to the net ionic? You would cross out your spectator ions, and that would get you to the complete ionic equation. Or if you're not asked for the complete ionic, you can do the shortcut. And I would say it's usually worthwhile doing the shortcut. It does save you time, unless you have 2 precipitates, in which case you might as well just do the complete ionic because it's the same thing anyway. Okay? How are we feeling about this? All right? Okay. So for homework, you're going to do these questions. All right? 3.1c. And we are going to move on to 3.1d, qualitative analysis. Ooh. This is on page 17. We have a beaker. Oh, and this is basically determining which ions are present. Qualitative analysis. It's called qualitative because you're figuring out what's there, not how much of it there is. So it's not quantitative, it is qualitative. And you do that by selective precipitation and other methods. Okay, so we're going to talk about what selective precipitation is. Selective precipitation is precipitating one ion at a time. Sometimes I find that it's helpful to draw a little picture for yourself so you can visualize what's going on. Yes? You don't have to do this, but it can be useful. So we have a beaker, and it contains calcium nitrate or lead nitrate or both. So I'm going to say, does it contain calcium? Does it contain lead? We don't know. It contains one or the other or both. So what we're going to do is we are going to find something that will precipitate either calcium or lead, but not both. So on page 4 of the data booklet, I want you to go and take a look and find something that will precipitate calcium or lead, but not both.
What do you mean by one that does what? What do you mean by both?
You want one that precipitates either calcium or lead, but not both of them. So would it be okay would I choose nitrate to precipitate calcium or lead? No, because it doesn't precipitate either of them. That would be a poor choice. Yes? So go find something that precipitates one of them, but not the other. Find as many choices as you can.
Sulfate is going to precipitate calcium.
Iodide. Could we choose iodide? Yes, because it would precipitate lead, but not calcium. Similarly, we could also choose bromide or chloride. They would work the same way. Yes? How about sulfate? Would sulfate work? It won't work because it precipitates both. Uh-oh, that's not good. So you don't want one that precipitates both. How about sulfide? Does sulfide work? Yes, because calcium is up top and lead 2+ falls in the all others category. We can check all the rest of them, but all the rest of them would precipitate both of them. So our choices then are chloride, bromide, iodide, or sulfide. All these will precipitate the lead, but not the calcium. Let's pick one. Which one shall we pick? Doesn't matter. Which one do you like? Bromide. Okay, excellent. Choose one at random. Is it possible to add bromide ions all by themselves? Can you go to the back room and get a jar full of bromide ions? What would happen if you had a jar full of bromide, Br minus, 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 Br minus, Br minus? What would happen? You'd have all those negative ions right beside one another. They would all repel and it would explode, yes? Ions do not come on their own. They are always part of an ionic compound. So all ions are part of an ionic compound. So you need a partner for the bromide ions that will not take part in the reaction. You want something that will not precipitate, that will not act as an acid, that will not act as a base, because acids and bases can cause some difficult side reactions. Will not precipitate anything. Not an acid. Not a base. Who could be a partner for bromide that we are guaranteed will not precipitate anything? You don't want to add Ca because you're trying to figure out if we have Ca. And if we add it, then we have it and we can't tell. You need what kind of an ion? Positive or negative? You need a positive ion. What are some positive ions that are always soluble? Oh, sodium. What else? Sorry? Lithium?
Any alkali.
Any alkali, yes. Anything else? NH4. But we have a little problem with NH4 because it is not because it's a polyatomic. You also need this thing to be not an acid. Go look on your acid table, see if you can find ammonium. Yeah, it's on the acids, okay? Don't choose it. Don't choose hydrogen, which is soluble with everything, because it is an acid, okay? So any alkali. Now let's be practical. Do you want to choose cesium? Cesium bromide, does that sound like a thing you're going to find in our back room very easily?
No, but potassium is
No, potassium is good. What's the most common positive ion that we come across? Usually sodium. Okay? Sodium is usually the best choice. So you don't even have to remember very much. You just have to choose sodium. If you need a positive partner for your negative ion, who will you choose? Sodium.
Are you gonna remind us tomorrow?
I'm going to remind you all through this unit. But should you be going home and reminding yourself? Yes, because next year, is your professor going to sit there and remind you of things all the time? Do you think that's likely? Or do you think they're going to say it once and assume that you heard it and that you learned it and that you're going to learn it on your own? They're going to do a lot of assuming. My first year physics teacher. This was back in the 80s when not a lot of schools even offered calculus in high school. Mine did, but you know, it was only differential calculus and we only did like the barest minimum. We went in there, first semester of physics, first week of physics, and he says, "Oh, you guys know how to do line integrals, don't you? No? Here, let me show you." And I'm like, what just happened? I've not even finished differential calculus course, and he's doing line integrals, which is like third year calculus. Yeah, so professors can make all kinds of assumptions. So you want to make sure that you are in charge of your own learning, okay? So we're going to then choose sodium bromide, NaBr. How much of this compound, NaBr, do we need to add? Well, we're going to need to add enough to precipitate out all of the lead, if there is any. Okay, so we don't complicate our next step, because anything that will precipitate calcium, and we still need to check for calcium, anything that will precipitate calcium will also precipitate lead. So if you don't get rid of all the lead, you will get a false positive for calcium. Okay? You want to precipitate out all the lead. Otherwise, the leftover lead will give a false positive for calcium. Because every single ion that precipitates calcium will also precipitate lead. So all the lead needs to be gone so you can check and see if calcium is present. So we need to add, and you don't need to be really specific about this. This is qualitative, okay? So all you need to say is we need to add an excess of the NaBr. Add too much, add more than you need to precipitate all the lead. And then we have really three choices of what's in our beaker. We either have just calcium, or we have just lead, or we have calcium and lead. What would happen if we added NaBr and we only had calcium? What if there was no lead? What would happen? Nothing would happen. Because bromide is soluble with calcium. So here, there's no precipitate. So what you're going to do is you're going to interpret the results of this experiment, and you'll say, if there's no precipitate, then there was no Pb2+. Yeah? If we add NaBr to the thing and it only had lead, what would happen? We would get a precipitate. And what if we added it to the one that has both? Yeah, we get a precipitate of PbCl2. Okay, so what's going to happen then is at this point, you're going to have a precipitate, and I'm going to make it blue, and I'm going to be like precipitate. Yes? So you need to make a statement at this point and say, if I got no precipitate, no lead was present. If I got a precipitate, then lead was present. Now we're going to add something that precipitates the calcium. Okay, so let's check and see, do we have calcium? Could you please find an ion that will precipitate the calcium? What do we like?
The three works. Chloride, bromide, iodine.
Chloride, bromide, iodide works?
No.
No, that doesn't work. That only worked for lead. How about sulfate? Does sulfate work?
Yeah, no, because it does both.
But what did we do already? We already got rid of all the lead. So we can use sulfate. Sulfate would work because the lead's already gone. So sulfate would work because lead is gone. What else could work? Sulfide could work. Oh, could it? No, sulfide can't work because it will not precipitate the calcium. How about hydroxide? Hydroxide? Give me a thumbs up or a thumbs down. Hydroxide. Chat amongst yourselves, and then we'll do a thumbs up and thumbs down. Does hydroxide work for calcium? Is calcium up here or is calcium down here? Down there. Oh yeah, it doesn't matter. OH is fine. You can use OH. You really don't want to use it in something that's an acid. Okay, yeah. In fact, let me get rid of that from our notes because I am incorrect there. Let's get rid of not a base. Okay, so let's get rid of not a base. Let's just make sure it's not an acid. Okay? Because almost all negative ions are bases except nitrate. Yeah? Phosphate is a base. Carbonate is a base. Hydroxide is a base. So yeah, we basically don't want to use NH4 or hydrogen. Okay? No NH4 or hydrogen. Or we could write that down too. So could we use hydroxide? Now that we're not worried about it not being a base, could we use hydroxide? Yes. Could we use phosphate, carbonate, or sulfite? Yes. All right, so any of those we could use, but we have a problem because if we add them, do you guys know what a precipitate looks like in solution?
It's like cloud.
It looks cloudy. Yes? Cloudy. Cloudy.
Is that what the first image you showed us, the yellow?
Yeah, the yellow one is a very, very vibrant precipitate, but sometimes it'll just look like white cloudy. Okay, white is the most common precipitate color. Now let's imagine that we now add some sulfate and it precipitates the calcium. I'm just going to draw what that looks like for you here. Oops. There we go. Watch. See how different it looks. Oh. So we have a cloudy solution, and if we add something that precipitates the next thing, we still have a cloudy solution. How are we going to tell whether it's really more cloudy? Is it more like, do you want to be making that judgment call? No. Wouldn't it be nice to get rid of the original cloudiness before we add the next thing? That's exactly what we do. Does anyone have any idea how we can get rid of the lead precipitate cloudiness? See if you've got any ideas.
Like
Physically, how do you get rid of it?
well, we just put it into some machine.
You just what?
You just put it like into the machine. So
The machine. What is that machine?
I don't know.
You don't know, but you know what it does. What does it do?
Like it just like removes like the solid.
It removes the solid. How does it do it? Okay, we'll bring out the machine so you can actually see it. So there is a machine that will do it, but there's also another way if you prefer. Anyone got any ideas how you can remove a solid from a liquid?
I don't need vacuum that.
You can filter it. Filter. The second way, and this is the machine you were talking about, is called starts with a C. Does anybody know it? Centrifuge, yes. You can centrifuge it. And if you centrifuge it, you also have to decant it, which means to pour off the liquid. Now, if I were doing this in the lab, I would do this one for sure because I can work with fairly small volumes, right? If you filter something, a lot of the water, a lot of the liquid gets stuck on the filter paper and it just sits there, and so you're losing a lot of your solution. Plus, have you guys filtered anything? How long does it take? An irritatingly long time? Yes? So I would do this one in practicality. For writing it down on paper, a lot of people choose filter because it takes less time to write. Yes? But I have a tendency to go with centrifuge and decant because I just know it makes for a better choice, right, in real life. Usually the better choice in real life. But you can pick whichever you want if you're answering a question. If you're like, I don't want to write centrifuge and decant, it is too long, you can write filter. So our solution is still cloudy with the PBBr2. How do we get rid of that cloudiness? We either filter it or we centrifuge and decant. So here's a picture of our centrifuge, and they've done this lovely job of like doing a cutaway view. So you can see you've got test tubes in there, and if you have the cloudiness in there, right, this thing is going to spin really, really fast. And if it spins really, really fast, what's going to happen to the more dense solid? The more dense solid will end up down at the bottom. Usually on the side, it'll end up looking like that. Okay, that's your solid, ends up at the bottom. And you can see here, they don't have a picture with a test tube, so I used this little doodad instead. We have the pellet, which is the precipitate. And we have the supernatant, which is the remaining solution. Now, if you centrifuge it, you need to complete the process of getting rid of the solid, and you do that by pouring off the liquid and leaving the solid behind. So this is how decanting works. We have our solid down here. We have our remaining solution here. This is usually a glass stirring rod. And the reason we use a glass stirring rod is, has anyone ever like poured things from a measuring cup and instead of going into whatever it is, it ends up on the counter because it runs down the side of the measuring cup? That's because water forms hydrogen bonds with little hydroxyl groups on the glass. Glass has hydroxyl groups. So there are intermolecular forces between the water and the glass. So it's like, oh, I'm gonna try pouring it out, but the water's like, oh, I'm just gonna continue to stick to this. But if you provide it an alternate pathway, if you have your glass stirring rod and you pour it, it will follow the glass stirring rod down and you won't end up with things like ending up on the counter or whatever. Okay. Our other option, of course, is to filter. Oh, and you should be familiar with the word to decant. So that is pouring off the liquid and leaving the solid behind. And now we have a solution that may or may not contain the calcium. Yeah? Now we're going to filter. Or, sorry, not now we're going to filter, or we're going to filter, or. This is your other choice. If you have a large volume, this is good for a larger volume. You pour it in. The solid, of course, stays behind here. Okay, the solid is called the residue. That's our precipitate. That is our solid. the remaining solution is called the filtrate. That's our remaining solution. And again, it may or may not contain calcium. So what we're going to do is we're then going to repeat the original steps, which is finding an ion that will precipitate calcium, pairing it up with a soluble ion, like sodium, and then we're going to add it to the solution, and then we're going to write a statement saying if it precipitated, calcium was present. If it did not precipitate, calcium was not present. And then, depending on what it asks you for, you can choose to centrifuge and decant or just leave it. Yes? So let us start by looking on the data booklet to find an ion that will precipitate calcium. We decided that we could use, what were some choices we had? Could we use phosphate, carbonate, or sulfite? Yes. Could we use hydroxide? Yes. Could we use sulfide? No. Could we use sulfate? Yes. Okay, so our choices were phosphate, carbonate, sulfite, hydroxide, or sulfate. Which one would you like to pick? SO3? Sure. Sulfite. All right. What's the next thing we should do? After we've picked sulfite, what do we have to choose? We need to choose a soluble partner for sulfite. Huh? Why don't we add NaCl? Because Cl will not precipitate anything.
You know, like touching this solution right now.
What would it do?
Yeah.
The lead's gone.
Right.
So there's nothing for it to precipitate with.
Yeah.
Why should we add sodium chloride?
Yeah. No.
Why would we do that? Yeah, we're not going to. Who would be a good partner for our sulfite? Sodium. Yes. Okay. Always choose sodium. Okay, so let's keep going. And so we're going to pair up the sulfite ion with the non-reactive cation. Sodium is always a good choice. And remember that we added an excess of NaCl to ensure that all the lead was removed. We want to add an what of Na2SO3? A lot, an excess of Na2SO3 to ensure all the calcium is removed. And then you make a statement, if a precipitate forms, calcium was present. If no precipitate forms, no calcium was present. All right, and since there were no other ions possible, you can just finish here. If there were 3 cations, you would then have to do what before precipitating the third one?
Oh, yeah, you gotta do the centrifuge.
Centrifuge and decant or filter, yes. we're going to try another one, but this time, instead of having cations, we are going to have anions. So we need a system. Devise a system. Often this language messes with students, right? They're like, devise a system? What? To determine if a solution, or they'll say design an experiment. What? That just means that we're doing this qualitative analysis thing, okay? To determine if a solution contains phosphate, sulfate, or both. So you need to choose an ion that will precipitate phosphate or sulfate, but not both. Could you please go find one?
Oh, it doesn't really matter what order we do it in.
It doesn't, but you will find that there is usually only one that will precipitate first.
Oh.
Because the other one will precipitate with both. Yeah.
Like for the first example
we did the lead first. Because in general, lead is a less soluble ion. It precipitates with more things. In fact, there's nothing that will precipitate calcium that won't also precipitate lead. So you really, you're locked into having to do the lead first. Okay, and you're going to find the same thing here. You have to do one of these ones first. Do you guys want to try this one on your own? Yeah? Oh, no? Okay. We need to find something that will precipitate sulfate or phosphate So we want something that's going to precipitate sulfate or phosphate, but not both. First of all, is it going to be an anion that we need to add or a cation? We need to add a cation. Could we use calcium? Calcium is in all others. So that's not going to work. Is there anything else we cannot use? Is there anything else we cannot use?
Sulfate is like everything bad.
We cannot use silver, right? Because it is also down here. We cannot use strontium because strontium is also down here. We cannot use barium or lead because those are also down here. Does that mean we can't use anything, or does it just mean we cannot use those 5? We cannot use those 5.
Oh, we can use any other.
Can we use any other?
We can use any alkali.
Can we use any alkali ion? Alkali ions will not precipitate phosphate.
But will for sulfate.
Will it precipitate with sulfate? Are my alkalis here? No. So can I use the alkalis? No, because the alkalis are here. What about beryllium? Well, beryllium is up here. Yeah, it's not one of those 5. Where would beryllium be for phosphate? All others. Is beryllium a possibility? Yes. Please find another possibility. You might want to look at your periodic table.
I think we should use ratchet for this. Oh, any.
Which one do you want? Iron. Let's make it iron 3+ because it's easier to come by. Yes. Could we do iron? Yes, because it falls in the all others category for both of them. Any others? Nickel. Does nickel work? Yep. A lot of transition metals. Also magnesium. Copper.
So it's literally everything but the alkali and alkaline.
Yeah, everything but the alkaline, 3 of the alkaline earths and the alkali metals. Okay, but everything else is up for grabs. You could use gold if you wanted to be really expensive about it. Okay? Gold, I want to use gold. All right, but let's just be practical. Let's pick, I don't know, iron. Yeah, sure, let's do iron, okay? So any cation except Ag, Pb, calcium, strontium, barium. Ooh, where'd it go? Where'd it go? Ah! There we are. Where did my red pen go? Ugh. Oh, it must be over here. No? Add. How do I add? I don't know. That's okay. I guess I'll write in blue. Sure. So for example, magnesium, iron, nickel, etc. And we're going to choose iron. Who could we partner with it? An unreactive anion. Anions are negative. Who is a very good unreactive, soluble with everything?
No.
Do we want sodium iron? No. We do not want it to partner up with a cation. We want it to partner up with an anion. We need a negative ion that is soluble with everything. Yes. Which one is it? NO3. It's always going to partner up with NO3 minus to make a compound. The best choice of an unreactive ion is always NO3 minus. And you will notice that NO3 minus is the conjugate base of what kind of acid? HNO3, what type of acid is HNO3?
Yes.
So you're not going to end up with any weird side reactions happening because you've added a base. Yeah? Yeah. So we're going to add how much? An excess learn that word. Do you see how we got numbers here? These steps, you're going to always follow these steps. You're going to practice these steps until you can do them in your sleep. Yes? Add an excess of what? NO3 minus? No. Add an excess of what? Like that? No. You cannot go into the back room and get a jar of Fe3 plus ions. What do you have to add? You have to add a compound. What is that compound going to be? FeNO3. So you need an excess of a soluble compound. Then you need the statement, if a precipitate forms, what was present? If a precipitate forms, HeO4 3 minus was present. If no precipitate forms, no PO4 3 minus was present. What do you need to do next? You need to centrifuge and decant or filter to remove the solid. W, X. Ooh, 2 L's make a W. There you go. Okay. So you're going to centrifuge and decant. What's our next step going to be? Now we need to see if we can identify if there was SO4 present. What next? So we're going to add how much? An excess of, right? And we need a positive ion and a negative ion together. And remember, we're trying to precipitate the SO4 2 minus. Who should we add? Who would be a decent choice to precipitate the sulfate? Let me get rid of all my scribbles here. Who could we use to precipitate the sulfate? Calcium or silver, strontium, barium, lead. Yes? Which one should we do? Calcium? Sure. Do we just add calcium? Calcium nitrate, yes.
we need like, if we need a cation, we just add nitrate.
If you need a cation, you add it with nitrate. If you need an anion, you add it with sodium. Okay? What do we do after we have added an excess of calcium nitrate?
Well, we just do the
Before you do that, you need to interpret the results.
But how do you know what happened?
How do you, no. You're going to say, how do you interpret the results? You say if. If a precipitate forms, what was true? SO4 2- is present. If no precipitate forms, no SO4 2- is present. Okay, so what I'd like you to do for homework is 3.1c and page page 20, number 1A and B.
Page 30.
20. Okay, so that's mostly just writing complete ionic, net ionic, blah, blah, blah equations. A couple of practice doing what we just did. And then tomorrow I'll give you some class time to do some more of those so that you can be checking in with me about how you're doing it. Okay?
No, it just goes back to equilibrium. We'll do like that. No,